Hello, welcome back. Yeah. Okay. Yeah, welcome back. Let's restart the session. We now have talk by Adam Hartshorne, who will be presenting his work on ArcFlow. Over to Adam.
Hi there. Okay, so this is a paper I published at 3DV this year. Okay, cool. Right, so the task is quite simple. We've got a source mesh and we've got a target mesh. And we'd like to try and interpolate, or we would like to try and deform the source into the target in a geometrically realistic shape interpolation. And we'd also like to learn the dense correspondence once we've done this. And in this case, we're not worrying about change identity, we're just looking at change of pose. And so we sort of started with some desired properties that we'd like. So we'd like to be invariant to surface parameterization. So we want to handle different numbers of vertices between the source and the target, different triangulations, be robust to sort of noisy data, so much more real world. You've scanned somebody, it's all very noisy. And for the interpolation part, we'd like to be as physically plausible for all these intermediate poses. And so what we thought was we'd like to have some hard constraints, which is preserve the topology. We don't want holes opening up or the mesh intersecting, self-intersecting. And if you're dealing with the same identity, volume has to be preserved. You can't sort of add extra mass to me as I move around. And so they're hard constraints. And we'd like some sort of soft constraints, which sort of tries to model how tissue deforms, how our skin stretches, in a very sort of hand-wavy kind of way. And what we said was the price we're willing to pay for this is to include a simple skeleton. It's not rigged, it's just some like joints and edges, just a very simple graph. Okay, so I should say as well that this task is surprisingly under-researched. There's a huge amount of work trying to learn the dense correspondence, and there's quite a lot of work trying to do the interpolation. But what normally happens is people either presume they have the dense correspondence, or they do the dense correspondence and then they do interpolation. They rarely do both together at the same time. And our sort of theory was that actually, if we are careful about how we do the interpolation, this will improve the quality of our dense correspondence. Okay, so there's several steps to this. First of all, we're going to define some sort of flow field between the source and the target. And the way we decided to model this was a diffeomorphic flow. And a diffeomorphism is a smooth differentiable map between two manifolds, which is both bijective and invertible. And this can be modeled by a vector flow field defined by an ODE. So rather than sort of learning vector offset vectors for each vertex, instead we learn a flow field that we put the shape into, and then that deforms the shape. So you're not directly impacting the shape. You're learning the world which will impact the shape itself. And anybody who's sort of familiar with this kind of maths will have seen neural ODEs, and this is which we did, which is you get your sort of a simple MLP to learn the function, and then you have a numerical solver to approximate the ODE. And this is the kind of flow field that you can get, and your shape deforms under this flow field. Okay, cool. And the advantage of what's going on there? The advantage of this is, compared to just learning vector offsets of each vertex, is these streamlines can't cross, so you're guaranteed that topology will be preserved. And also you can construct different types of vector flow fields. So if you take the curl of a function, A, we can preserve volume by construction. So that's kind of ticks off two of our requirements. Okay, so we're sort of learning to deform this source to the target. And we said that we were willing to add this simple skeleton. And so what we're going to do is we're going to estimate the rigid transformation for each bone in this skeleton. And the way that we're going to do this is we're going to put samples on each of the bones, and we're going to pass those samples under the flow field to find out where they flow to, but also learn the rotation angles or optimize for them, and those two should line up because rigid components can only undergo a rotation and a translation. And so why do we do this? Well, it's designed for this physically plausible interpolation, and articulated creatures have this, we know they have this internal skeleton, so sort of, and what we found as well is if you try and do this matching without correspondence, it's quite easy to actually match locally similar parts, which are actually the wrong part. What is going on with that thing? Whereas if you do this idea of having the skeleton with some samples on it, and we push these samples through and match those to the rigid deformation, so the rigid transformation, we can ensure that this locally similar parts, so that the right parts match up. Okay, cool. We can also extend this further by sampling not just the rigid parts, but also tissue samples, skin samples, and we optimize this under a framework of continuum mechanics and sort of beyond the scope of this talk, but it's the same idea that we basically take some samples in the volume, we push them under the flow field, and we have some loss put onto those to ensure they try and give us the properties we'd like. So as rigid as possible, Mobius as possible, things like that. Okay, cool. And so now we can deform this source to the target, but how do we know how well we're doing? So the way in which we tackled this was to evaluate the shape alignment using a thing called varifolds. And varifolds are a metric from geometric measure theory, which is quite a mouthful, and it's a little bit beyond the scope of this talk to go really into detail, but I'll try and give you a hand-wavy motivation. Okay, so you can think of shape as what's left after accounting for global transformation of a shape, of a surface. And we can model an oriented surface as a vector field. So we have a load of points, the normals, and we can think of modeling that as some sort of vector field. And the idea is that if your two shapes are aligned, those vector fields will be very similar. And what you can do is you can form a discrete approximation to this. And I don't have time to kind of go into it, but the intuition is basically you have a spatial kernel and a normal kernel. And what it effectively says is, in space, if 2 points are close in space, their normal should align. And the beauty of doing this in this way is it doesn't matter how many points we have in the source, how many we have in the target. They can be different numbers of points. It's very flexible in that respect, which again ticks off one of our desired properties. And once you form these kernels, you can define a discrepancy matrix, which tells you how close these vector fields are to one another. Okay, cool. Right, so then some mandatory qualitative results. And basically we tested on 3 common data sets that you've probably all seen. And we beat all of the existing methods, both in geodesic distance of how close our dense correspondents are to one another, the chamfer distance of how well our deformed mesh meets the target, and how conformal the mesh is as it's being deformed under this flow. So I should also say that SMS is a functional mapping based approach, which is quite a standard way of doing dense correspondence. The ESA is another varifold based method, but doesn't have these extra constraints like the skeleton. This is why I found it quite important to use. And then the other two are similar methods for the flow field, but they try and match using chamfer distance, which is a poor metric to try and compare two surfaces. Okay, so graph's great, number bigger, and this number, this AUC, is area under curve. And so what you do is you take your points and you threshold how many points are within a certain value, and you draw your curve up until you get to 100%. And so, yeah, but what does that actually mean? So let's have a look at some of these results of how our method is better. So we can see here that when we do this hand deformation, the SMS method, you get this kind of flattening, but because we're doing this sampling also in the volume and then putting these extra continuum mechanics, ours doesn't have this flattening going on. So you get this nice interpolation between the source and the target. And another sort of characteristic of some of these interpolation methods is what they call like rubber hand. So the arm moves quickly and the hand kind of shakes along, and ours doesn't suffer. It has a nice smooth interpolation. And another thing with our method compared to the SMS is when you look closely at these correspondence, we have this very smooth map where even if we are off by one sort of vertex of where it should be, there's a continuous map that is all organized. Whereas if you look closely at some of these functional mapping methods, all bets are off and you can have correspondence which are crossing across one another. So there isn't really a smooth mapping between the source and the target. And then we sort of got some of these more difficult examples where there's been a large deformation between the source and the target, and we fit quite well, and low chamfer error and high quality of dense correspondence. And that's kind of all I've got to talk about. That's our project page, and then I think Neil will probably kill me if I don't give the obligatory advert that if this kind of stuff seems interesting to you, we do have some postdoc positions available. So come and talk to me or Neil if you'd like to know more. And that's all I've got to say, I think.
Thanks, Adam. Questions?
Really nice work. Obviously, it makes sense that it would improve the results. I had a question. So, since the purpose is to potentially align a pose template mesh to a scanned person in a different pose, is there any assumptions about the quality of the meshing of the scan? Like, should it have no holes and should it be smooth and like got rid of noise and stuff like that?
Yeah, so that's a great question. So the standard varifold formulation is very robust to noise. It's less robust if you've got big chunks missing out of it. However, there is a way of dealing with that. I don't know if I'm allowed to say. There is a way of dealing it, and so you can, under this same framework, you can formulate a slightly different metric which will be robust to scans which have holes in, or but the base varifold formulation is robust to a lot of noise, surprising amount.
Very impressive. Thank you.
Just wondering what applications there are for the neural flow field once you've done the alignment. Like, I presume you've done the alignment, now you can just throw it away, right? Because you've aligned your mesh. But is there anything you can do with a neural flow field outside of that fitting?
So obviously the idea is that you could also do interpolation, but the thing about the neural flow field as well is that although we're pushing through those samples, I can give you other samples on the surface, and I can push those through if I want to. So it's not learning just simply here is a point going here. I can sample anywhere now on the surface and push those through. I don't know if you wanted.
Oh, I've got a few ideas. I'm not going to tell you now.
If no further questions, then let's thank Adam once again.
Got that.
the